Good afternoon. Hope you enjoyed the lunch. It's always great to see the Santa Clara crowd. My name is Mike Resso. I've been with Keysight Technologies for about 20 years now. Started back in Hewlett-Packard Lightwave division with Jeff and Rob and some of the other folks. So I've had the pleasure of working with these other speakers for quite a long time. I'm the signal integrity application scientist, and I work in the Internet Infrastructure Group in Santa Rosa. And so what I'm going to be talking about today is a kind of a new measurement called COM, stands for Channel Operating Margin. You may have heard of another COM, which is Common Object Model. It's a programming thing, and that's not what we're going to talk about. But I'm pleased to be here. I've written a book on signal integrity with Dr. Eric Bogatin, and so at the end of today's talk, I'm going to have a little pop quiz and give some of these out just to make sure that you guys don't fall asleep after eating lunch, which is always a challenge. So a little extra incentive there. So with channel operating margin, it's sometimes referred to as the Rosetta Stone. It's a new standard that's unifying transmitter, receiver, and interconnect all into one figure of merit. So in a way, it simplifies a lot of things if you're not used to S parameters or S parameter measurements or return loss, insertion loss, which is better or worse. This is a nice standardized proposal from various industry standards members. So it was a collaboration between both the silicon engineers and the platform engineers working together, which is something that not always happens, right? So this is something that hopefully will make things more simple, but as with any tool, there are complications that we have to be aware of, and I'm going to talk about some of those. So what is COM? It's a complete channel characterization, so you will have many variables, and the output from COM is one number in decibels. It first started being used in various degrees around 2000 for KR testing for backplanes. Some of the gentlemen involved in the early development, Richard Melitz from Intel started. Richard now is with Samtec, and I wanted to acknowledge his help for developing some of the slides that I'm going to present to you now. It's rather new material. This is the first time I've shown this. And Richard was very helpful in helping us straighten out some of these challenges. So again, the whole idea here is it takes the transmitter, the channel, and the receiver all into account. Now, it may prove beneficial to different engineers in different ways. If you're a SerDes engineer, serializer, deserializer, chipset guy, gal, it's a reference chip capability that it gives you, standardizing things like preemphasis and equalization, and it gives you a signal-to-noise ratio budget for a receiver. Now, if you're a channel engineer designing interconnect, backplanes, cables, connectors, whatever, this will give you a budget between insertion loss, return loss, reflections, and also crosstalk, near-end and far-end crosstalk. So all of these parameters are taken into account and given different weights so that you can come up with one rule of thumb, which is a nice, easy rule of thumb to start analyzing the complete channel. So it's also a very valuable tool if you're a channel engineer for design trade-offs between, what kind of via stubs do I want to avoid, what kind of exotic materials can I use, or what standard materials can I use, what design methodologies where it's microstrip, strip line, and then what type of connectors do I need. So it'll help you do a design of experiments, if you would like, during the prototyping phase. So where is COM being used today? As I mentioned, it's rather new. There's IEEE standards that are starting to use them. There's more proposals that are going around these various organizations. 802.3 BJ is one of the first that started implementing this for 10G based KR channels. Also, the 802.3bs, there's draft standards in there. So any place where you think of these very fast data rates, 200 gigabits per second, 400 gigabits per second, all these forward-looking standards are ones that will be contemplating using this channel operating margin. So if you can get a little bit familiar with this now, then you can be ahead of the curve when it starts to be adopted by mainstream. In my opinion, it's not quite mainstream yet, but this is okay. You know, we all need to be kind of a half step ahead of the mainstream to be successful. So why use COM? Who cares, right? That's a question, you know, practically you need to ask yourself. Well, what it answers is, are all specification failures equal? All S parameter failures, are they equal? Well, let's give you a simple example. I've got 3 different differential backplane channels, and it's a 100 gigabit Ethernet application. Each one fails for a different spec. The first one fails return loss by 3 dB, second one fails insertion loss by 3 dB, and the third one has a crosstalk problem, and it fails by 3 dB. Which one is the worst case channel? They're all failures, right? But they're not all created equal. Not all failures are created equal. And the answer is it depends. So COM will take all of these various failure mechanisms and it will give standardized weighting to each one. And it'll tell you some number in dB, and of course, it's a positive figure of merit. The bigger the dB, the better the channel performs. And if anything else, it gives you a very good standard relative performance between many different channels. And this is a very useful thing. So how do we test COM in the physical layer? Well, so we're going to be measuring interconnect, linear passive interconnect, with either a vector network analyzer or a time domain reflectometer. I don't think we have a VNA here today, but we do have a time domain reflectometer back here. Jeff's got a really nice demo going here with a 5 picosecond rise time step from the TDR. So the crosstalk that needs to be measured means it's not just a simple 4-port S parameter measurement, right? If you have a differential channel, you've got 2 input, 2 output, that's a 4-channel or 4-port VNA measurement. But remember I said crosstalk is taken into account for COM. What that means is this is now going to be 3 differential channels, 6 input and 6 output, so the minimum number of ports to do a COM measurement is 12. Okay? Now, you're probably thinking, well, heck, I don't have a 12-port VNA in my lab. Well, you could. I mean, we've got up to 32 ports available on a Pixie chassis, we'll talk about later, but there is a way to get a 12-port measurement with the 4-port VNA, and it's something called Round Robin. And it's a software tool that's inside physical layer test systems, and it'll allow you to follow directions of how to connect the 4 VNA ports sequentially to all of the 12 ports on your DUT to get a 12SP touchstone file, and that's what's input into the COM routine. So the COM routine is a MATLAB subroutine that's been written by the standards committees. So you can use this default MATLAB script. It's 200-300 lines of scripting, and by importing into a tool, running the MATLAB script that's standard for COM, you can get the number in dB, which I'll show you. We'll do a quick demo here at the end. Now, one of the things that you can do once you become familiar with COM and you want to start to do these design of experiments, there's a configuration spreadsheet that's designed in Excel by the standards committees that's given out free with the MATLAB script, and each cell in the spreadsheet can be modified so that you can run COM on a design of experiments. Maybe you change in one space the bit rate, 10 gig, 20 gig, 30 gig, up to 100 gig. Then in another space, you run more and more crosstalk, and you can do comparisons. And it's done inside this spreadsheet. So you don't have to be programming, per se. You can leave the MATLAB scripting as is, and you can just modify the spreadsheet. So it's actually quite convenient. Publishing the results is very easy if you have the right software tools. And even if you don't, it's just running MATLAB script. So this is something you can all do. And the idea is you want to publish the results and then optimize the physical layer so that you can enhance the COM number. The bigger, the better. So where is the COM test points? So looking at this standardized drawing from one of the IEEE specs, it's between TP0 and TP5. So you can see TP0 is at the BGA to board plane for the transmitter, going through all of the channel and interconnect, whatever it may be. And then you're measuring at TP5 right before the BGA of the receiver. So of course, when you have a full 4-port measurement or full 12-port measurement, the machine, the VNA or the TDR automatically sequences the input stimulus, reading the output on all other 11 ports, then switching the stimulus automatically, and then reading the other 11, and just rotating that way, and that's how it gives you a 12-port S parameter. So how many cells in a 12-port S parameter matrix? 144, right? So a 12-port S parameter it's a 12 by 12. A 4-port S parameter measurement has 16 elements, right? Differential in, differential out, common in, common out, and then quadrants 2 and 3 are your mixed mode S parameters, okay? Very good, by the way. Who said that? Here, could you pass that back to the gentleman there? Thank you. So when you run COM with physical layer test system software, which is a Keysight product that drives either a VNA or a TDR, you can have up to 32 channels. You only need 12 channels for COM, but as I mentioned, we know that there's crosstalk terms, and you can add more crosstalk aggressors if you choose. It's not necessary or required, but this may be something you want to do. We know that crosstalk varies as 1 over the distance squared between the victim and aggressor. So as you move away from the victim, the crosstalk is going to have less effect from an aggressor that's further away, but you can still choose to do that if you'd like. The nice thing when you have an environment like physical layer test system software that I'll show you, you can do port reordering. If you measure the ports improperly for whatever reason, you don't have to start over. You can just reorder the port number. You can interpolate existing SNPs. You can extrapolate. You can truncate. You can change frequency ranges. You can do all types of de-embedding, including automatic fixture removal. So there's all of these benefits that go along with measuring S parameters that you can utilize on the way of doing your COM characterization. So really the data management and manipulation is a huge help when you've got some software to help you out. I mean, if you've ever tried to manually create a 12-port S parameter file, it's really challenging. I think I did it one weekend, and I thought it was going to be an hour job, and it took me 8 hours, and it wasn't even right when I was done. So this is something you can save a lot of time on. And then you can read this later on. This is one of our quotes from a local applications engineer, Luis Baluna, I asked many AEs locally, how do you use COM? How do your customers use COM? You know, what kind of interesting feedback can you give me to share with our seminar? And so there was some interesting perspective that I'd encourage you to read later. So what do the COM results look like? So after you run that MATLAB script and you display all of the parameters that are output, this is what it looks like. You have CTLE response, you have a probability distribution function for the COM number itself, and there you can see I ran 2 cases, one with a package and one without a package, and the number 8.5 dB and 8.1 dB. This is extremely good. The pass-fail number's around 3 dB, and we actually created a simulation in ADS of a S12P file. That's why this number and value is so good. Normally, it wouldn't be this high. And all these other, there's pulse responses, voltage bathtub curves, equalization effects, pulse responses, throughs, insertion loss deviation, insertion loss to crosstalk ratios. So some of these parameters you may be familiar with already. And this is something that pulls them all together into one figure of merit. This is just an eye test, but really what it is, it's a parameter list. These are all of the things that you need to input into the COM MATLAB script. And when you use that pre-configured spreadsheet I mentioned, it automatically drops in standardized values for each of these. But you can just go through and read. These are all things that have to do with the complete channel, both the active and passive components. The bit rate, required frequency, start and stop, step, device package model, transmitter receiver, next, fext, single-ended differential, a lot of CTLE going on. So these are all very complex things, but because it's a standardized configuration spreadsheet, it's easy to use. You can get started very quickly and learn as you go. So the foundation of this channel operating margin figure of merit started with some of these things that you might be familiar with. Of course, return loss, insertion loss are just basic fundamental S parameters. Insertion loss deviation, this was just a way to see how much deviation there was inside the insertion loss of a particular channel. A little more mathematical, but not too crazy. Insertion loss to crosstalk ratio. You know, this is something that gave you a signal-to-noise ratio that was benefit looking at the insertion loss. So this is how it started, and it finally came to this final MATLAB scripting and configuration spreadsheet that we have today. And this is what the configuration spreadsheet looks like. This is the one that's given out for the 25G base KR, 100G base KR examples. And you can see these little tiny red triangles in the upper right of some of the cells. These are actually comments that are made by the originator. So Richard Mellis and some of these other gentlemen that were in the early stages have made notes, so you can actually learn while you use this. So what are the challenges, right? All new characterization techniques have challenges that we overcome as engineers, but it's nice to know what they are ahead of time if you can plan for it. You do have to run a MATLAB routine. So if you're using a standardized program like physical layer test system that will call MATLAB, if you use that environment and wrapper, then you can run that MATLAB code simply with the DLL that's provided with the PLTS license and installation software. Now that's not a challenge, but if you decide after you become an expert at COM, you've moved the variables and done your design of experiments in the configuration spreadsheet, you may want to jump into some of the MATLAB scripting. And in that case, if you want to do some MATLAB script changes for your own internal development, then you'll need a full MATLAB license. But if you're wanting to do that, you probably have the license anyway. Like any standard, you have to be up to date to see if you've got the latest and greatest. And when you communicate to colleagues and vendors and customers about COM, you should ask them first thing, what version are you working off of? Because it can make a difference. And the complexity, you know, it's a double-edged sword. The simplified programming does give you a quick reference. Using these default values is a very simple way to make comparisons that are relative to each other. But you really have to use good engineering judgment with your tools. Know what assumptions that you're making. Know the limitations of the tool. And any tool from any vendor, including Keysight, has limitations. And anytime I talk about my tools, I try and give the benefits, but also what are some of the downsides, what are some of the things I have to be concerned about that really are a limitation of that tool. So you have to be aware of those. So in summary of the slides, I'm going to give a quick summary, and then I'm going to do an actual demo for you so you can see what it looks like. So we talked about channel operating margin being a fast and efficient way to assign the single figure of merit. And it's for all interconnect channels, transmitter, media, and receiver. It does both time domain, frequency domain, statistical analysis, and it's just an evolution from some of these insertion loss deviation and insertion loss to crosstalk ratio calculations we've done in the past. So it's a very straightforward evolution from those. And it is a mathematical representation using computer code. So it's a nice framework to start with. I think that the standards committees and engineers have given us some good tools to start with. PLTS 2017 is an SI tool that does simplify the COM analysis. We just added this capability that I'm going to show you in a second at DesignCon in February this year. And if you want to learn more details, here's a website for you. So before I go into the demo, here's the marketing slide. So of course we'll help you when you start working with COM and transitioning to use it effectively, whether you're measuring it with the VNA or a TDR. And when you use the PLTS software, we've got experts locally and us in the factory can help you do this. The interconnect test system, RS506, is this reference solution that includes this PIXI VNA on the lower right. And each one of those modules, the PIXI module that's standardized, is a 2-port VNA. And you can basically pick whatever frequency range you want to take your VNA measurements, 3 gig, 6 gig, 9 gig, up to 26.5 gigahertz today. And you can go from 2 ports up to 32. So this will handle the 12-port VNA measurement that you need for COM. And then the DCA that Jeff has back there has TDR plug-in modules that you can have up to 16 channels. Right, Jeff? Yes, sir. Yeah. So here's a few acronyms that we talked about. And so let me go ahead and run the demo now. Any questions? Yes.
Is the 12-port sufficient to cover a high-density backplane connector, or is there a simplification step?
Good question. So the question is 12-port measurement adequate to cover things like a backplane connector? So looking at the way some of these backplane connectors are manufactured and designed, there's a differential pair pin, and then they have maybe 2, 4, 6, 8 pair running around it. So spatially, you might want to do more than 12. In that sort of situation, I think I would use the 12 standard COM configuration spreadsheet, but then I would go ahead and say, you know what, I know these other channels are going to give me crosstalk just by looking at the geometry of the connector. So I'm going to do a higher port measurement, or I'm going to use the round robin method, and I'm going to create a larger S parameter file from smaller S parameter measurements.
So you don't just need so 12 isn't always how many ports you have for the COM.
Yeah, I mean, when I was talking to Richard about this application, it's such a new concept to be standardizing a relative figure of merit, because really you have nothing to compare it to. There's another FOM like it. So I would always start with 12, but then I would start asking questions, and I would start talking with these standards committee members like, look, in this situation, I know that the same distance from this victim are 2, 4, 6, 8 different channels that could be aggressors.
Or does the solution take those other channels and combine it into one in the 12 port?
that could be possible. I think that the configuration and the geometry would be different. Yeah, so, yes. Oh, this is really good input. So this is the first time I'm hearing this. So the total number of ports that you've read in the latest standard is how many differential channels?
If you are considering 100 gig CR4 or KR4,
yeah,
then it's 4 TXs and 4 RXs. If you go to 200 gig, 400 gig, then depending on whether it's by 8 or by 4, it changes.
It changes. Okay, so there's your answer. So it's going up from 12. Yeah. Thank you. Thank you. Here, that deserves one of these too. Thanks. Yes.
The MATLAB code can be running on code tape, which is license-free, compliant to the MATLAB environment?
Yes, yes. You can run the MATLAB script on your own, and you'll just have some way to display all the results and plot them. In the way we're doing it with physical layer test system software is we have a wrapper that displays S parameters and time domain parameters and does that easily. If you've got another tool you like or you want to do it yourself, you can do that. Well, so let me show you how we decided to implement COM with physical layer test system, and then you can decide if this is something that you think would be useful or not. You know, the trouble of being on the bleeding edge of these tools is that sometimes the first drop doesn't have all of the features that you expect, because while you're developing code, sorry about that, while you're developing code, the standard's changing. So when you first start physical layer test system software, it's going to look for instruments because you can use it in the lab to calibrate and measure with a VNA or a TDR. But you can also do post-measurement analysis in your cubicle. So, of course, right now I don't have any instruments hooked up, so it's telling me, you know, hey, you don't have any instruments. I'm going to say, that's fine. I'm going to do analysis only. And I'm going to run it in virtual mode. And in this case, rather than do a new measurement, because I'm not hooked up to hardware, I'm going to load a measurement. And the measurement that I want to load is actually this ADS simulation of a 12-port measurement. And so it's an S12P, but as we're learning today, it can be even higher port count. But let's start with this S12P, and PLTS will allow you to look at this in either time domain or frequency domain, single-ended or differential. You can look at eye diagrams. You know, all of these domains that you can convert S parameters to and from with FFTs, IFFTs, convolution, pulse responses, bit responses. We can do all of that mathematically. I normally start in time domain differential just because I'm a time domain engineer. So the next step is we go to Tools, and Channel Operating Margin is a drop-down item there. And for this, we get a dialog box that is our multi-channel simulator. And the first thing that it wants you to do is tell me, where's your Excel spreadsheet configuration file? And so I'm going to go and browse that. And the standard one that I'm using is this one here for 100 GBase KR. And then here is a graphical representation of my 3 differential channels, the 12-port measurement. And I'm going to drop a differential transmitter on the victim and a differential receiver on the victim. And then I've got these differential crosstalk terms that generate crosstalk. And I'm going to generate fexed and next like this. So now I've basically got the configuration, I've got my crosstalk aggressors, and now all I need to do is call the MATLAB routine. So I press this button that says call MATLAB, and so it's going to call MATLAB in the background. This is a DLL, so you don't need the MATLAB license. It'll give you some of the nomenclature in the code header. It'll give you some idea of what it's doing. Right now it's processing the channel operating margin, doing some linear equalizer. Now it's looking at the probability distribution function of COM. The first near-end crosstalk, now the second near-end crosstalk. And so all of these plots are being run live. This is not canned. It's generating these on the fly based on how you have configured your Excel spreadsheet. So the result for my two cases is 10.7 dB and 10.5 dB. And here, underneath here, are all the different cases and plots that were flashing in front of your eyes previously. So this is the kind of showing how you would run the pre-configured COM. Now there's even a faster way to automate this if you want to create a template. In physical layer test system software, you can create a pass-fail template for any type of standard like SATA, DisplayPort, Ethernet, PCI Express, and you can insert whatever margins you want for your time domain waveforms, your frequency domain waveforms, your eye diagram masks, and save that under one template. And so we've done that for COM, and so an easy way to run that is to come to our template view and just run COM. And so now basically it's going to run the same exact code with the same spreadsheet, but now at the end I saved all of those plots that were flashing so that we can take a look at them at each one separately and do any kind of comparison that we want. How am I doing on time? 5 or 10? Thanks. So here is all of the plots that we talked about. You can zoom in on any of these. You can auto scale and compare these, save the results. So it does take a rather complicated MATLAB program and pull it together in an easy-to-view display. Yes?
Your cost something, is it power sum or individual?
It's power sum. Yeah. Yeah. Good question. So now, if we wanted to, what we could do is we could go into that configuration file, and we could change some of the values, like put a higher bit rate, and the numbers would change. And this would be that design of experiments that I was mentioning. So you have your 12-port or N-port, let's call it an N-port touchstone file from whatever device you have, and then you can change the bit rates, look at the COM numbers, and see how it changes. So this, I can see how this could be a very useful tool, whether you're a SerDes designer or you're a channel system integrator, interconnect designer. So I think that for a brief introduction, I think this is a good start. Yes?
From a high-level point of view, this is all like the old StatEye, right? And it's all linear math, given a source impedance and a destination impedance that must be in the files that you provide as your transmitter and receiver, or it only has its own model for a transmitter and a receiver?
Good question. So StatEye is something that was developed maybe 10 years ago that was another figure of merit that was actually trying to accomplish a very similar thing, looking at standardizing a complete channel. As far as I know, it's all linear systems. So linear time invariant systems is my assumption in this. For this work here.
So if I had a transmitter that had a different output impedance when it's transmitting a low versus transmitting a high, there's no, that's not handled. Is that?
You know, to be honest, I'm not exactly clear on that receiver question. So what I can do is I'd love to know the answer myself. So let's chat afterwards, and I'll talk to Richard, and we'll get some answers. Yes?
To give you a little bit of context on that. It assumes the worst possible transmitter that is compliant to the IEEE specification. Assumes the worst possible receiver compliant to the IEEE specification. So there's a reference receiver and a reference transmitter defined in the IEEE specification. That's what's implemented in the tool. It does not represent all possible cases. It represents what the designers of the specification consider to be the worst case.
Thank you. Okay, so I need to give away a few more books here, so I've got 3 more questions. What physical layer components are characterized by COM? Answer 1, 2, 3, or 4. All of the above, right? What test equipment is used to measure COM parameters? 1 and 2, that's right. What does PLTS stand for? Physical Layer Test System, PLTS. What methodology allows a 12-port S parameter to be created from a 4-port VNA measurement? Round robin. You guys are too smart. You know all the answers. That's all I have for today. I'm going to hand these out to a couple people that helped me with the presentation. Thank you all very much. I appreciate it.
Talk about compliance boards a little bit, and then we're going to go into the individual standards that I'm going to cover today. And I'm starting with electrical. I'm going to finish up with some of the optical measurements. So just want to talk a little bit about compliance test boards. You've already heard in the earlier presentations today that they're used quite a bit in the compliance testing. That's what I was looking for. And their function really is to give you a breakout, because if you're dealing with a physical chip, you can't really attach test signals to the balls very easily. So the standards realize that, and they create these boards. And there's 2 different types of them. We'll go into that a little bit later. But they basically break out the signals, and they're tightly specified in the standards. And for the most part, you have to de-embed. Now, different standards do it different ways. Some standards still refer you to the ball of the IC package is where the measurements have to be de-embedded to, and others de-embed to the connector in the compliance test board. So you just need to study the various standards. As time goes on, they're moving more and more to de-embedding to the connector on the compliance test board, which makes life a lot easier. And then they just tightly specify the S parameters of the board itself that you either purchase in one case or fabricate yourself, design and fabricate yourself. So, and be sure you test your board before beginning. It kind of goes without saying, but you'd be surprised. I've worked with some IC designers that have gotten far along in their characterization work, and then started seeing some non-repeatable results and said, boy, I wonder if our compliance boards are in good shape. And that's when they went and validate the compliance boards and found out that they were not actually designed to the standards. So before you start doing any real work with them and taking a lot of data, it's a good thing to validate the board itself. And that includes the purchased ones. For the ones that you can purchase, which are the basically pluggable optics boards. You would think that those are all, Rob mentioned in there that various companies have different performance levels, and we won't mention names, but they're not, even if they come with data, that does not necessarily mean that the de-embedding was properly done when they characterized them. So it's worth your while to take a few hours in the lab and validate the boards before you do a lot of work with them. So. Coupling is really important parameter now with PAM4 that in the past we haven't had to worry about with the crosstalk so much. And they don't specify the This is one of the parameters that's not specified in that. You might think, well, that's really kind of strange. How do you do that? But as you see when we get into the stress calibration, there's procedures done to essentially back that out, the effect of the crosstalk in the stress calibration. So, okay, so when we're dealing, there's basically two methodologies were used on input testing, and that has to do with the standards that, again, around pluggable optics. So it's chip to module standards, and IA, that stands for Implementation Agreement. OIF, their documents are called implementation agreements as opposed to standards. And all of these have a very defined physical interface because the optics itself, you know, that's set by an MSA, so not only is a mechanical package and connector specified, but the pinout is specified. So you might think the same holds for backplanes, but it doesn't hold for backplanes because that's a user-defined connector or an application-specific connector. So in those situations, you have to fabricate your own boards. But when you're dealing with chip-to-module that environment, the boards can be purchased. You don't have to design them yourself. So, and there's two boards in this application. There's a host compliance board, which emulates the module. So obviously this looks like a module, except here's a breakout. That's what plugs into your Ethernet switch or whatever your host is. And then the opposite end of that, if you're designing a module, you need to have something that looks like the switch, and it breaks out all the signals so you can characterize it. So that's the module compliance boards. And the S parameters are given as a mated pair, okay, which makes it a little bit tough, is how you do the validation. You got a little bit of work to do. But the standard specifies, it assumes an allocation for each board, and that's based on the fact that you actually have longer trace length in the module than you do in the host. So that assumption's made when they write the standards. So, okay, the test points are all defined. You'll see those all the time, TP1A or TP1, and the different standards have different numbers. You study those. It's usually in the early pages of the document, and you run with those all along. So again, we're dealing with de-embedding the board. So all of the signals are measured. If you're doing output measurements that Rob covered, you know, your responsibility is to de-embed the cable or system up to that test point. Okay, and then if you're dealing with input testing, where we're dealing with a stressed eye, then you have to calibrate your stress right here at where the signal enters the board. Okay, so TP1 or TP4A. Okay, and then the second situation is where we have a chip-to-chip or cable or backplane. We don't have a standardized connector, and in those cases, you have to design and fabricate the board yourself. Okay, so again, the S parameters are given to you in the specification, and you need to make sure that the design is compliant with the boards. And there is an exception that if we're dealing with, like for OIF MR, for instance, medium reach, that covers passive cables, and the outputs of those cables happen to be, you know, follow an MSA because they look like an optical module, right? But so there you do have the defined interface, but the MR standard assumes you don't. So even though you're going to be purchasing the compliance test boards, the test methodology is going to follow a methodology that assumes that it is not a breakable interconnect in the compliance board. So, and there's considerable differences when you read through the testing methodology, and you'll see that real quick when I start talking about chip-to-chip and chip-to-module, that there's considerable differences in the input test or the stressed eye test between the chip-to-module case and the chip-to-chip case. Okay? So now that's any questions or comments on compliance boards before I actually start jumping into the real standards. So I'm going to start with the electrical situation. So AUI is attachment unit interface. Basically, that's the electrical interface. So this is primarily, 802.3bs is primarily an optical standard, but it does also cover the chip-to-module case as well as the chip-to-chip case. So this is a host input test. All is done with a series of 5 stressed input tests. So they're combined. They do not have a separate interference test and jitter test as some of the longer reach standards do. So everything's combined. It's a very conventional or classical stress recipe that includes sinusoidal jitter, random jitter, and budge. Okay, now it's kind of interesting. I don't know why budge is still put in there. I think it's because they don't want to put a lot of SJ in the system. That's periodic jitter. Remember, this periodic jitter that is not correlated to the clock causes problems for decision feedback equalizers. So they want to keep the level of sinusoidal jitter down. So they need to put something else in the jitter mix to get the right eye closure. So that's why budge is still there. But the reason I bring that up is budge is primarily used to emulate crosstalk, and all of the new standards do no longer rely on budge being injected into the victim lane, but they actually use real crosstalk. In the past, we didn't put crosstalk aggressors in, and we relied on budge. But when you do that, you're making assumption in your device under test of what the coupling paths are. You know, how much coupling do you have? And that's a very dangerous thing to do, particularly with PAM4, where we're very susceptible to crosstalk effects. We don't want to make that assumption. We actually want to do the real test. So in the case of this standard, we have the 5 tests, and they're basically the only parameter that's being swept for those 5 tests isn't being swept. It's 5 static different tests, and that's the SJ frequency. And if you can see, we're kind of going around. We're doing a classic POL tracking test. So we at low frequencies we have very high UI, 5 UI, and then we jump down to the 50 milli UI at the higher frequencies. So we're just trying to test the POL tracking and the device's clock recovery. Okay, and then they start out with a specified amount of budge and random jitter, and that's just the starting point. At the end, when you go through all the fixturing and everything right again at that compliance test point, which is convenient because remember I showed that's right on the compliance test board, and that is a removable connector. So all you do is simply remove that connector with a cable and hook it up to your scope you're using to calibrate your stress. And there's no extra de-embedding or anything that is necessary to do. You can just calibrate your stress on the scope. And the very last step you do on some of these is to go in and adjust the RJ as kind of a padding number to get a specified eye closure. So at the end, rather than having just fixed SJ, budge, and RJ, at the end, it is a amount of eye closure is what the final requirement of the stress for this particular test is, okay? So now this is really key. Reference receiver is used for stress calibration, and you'll see on the next diagram, there's a big difference between the 100G class specifications and the 400G with that reference receiver, and it's very important that you don't miss that point, and it's the fact that it has a CTLE in it. Okay, and then crosstalk is applied counter-propagating direction. And it's very important that you have that CTLE in there, because if you don't put that in your reference receiver that you use to calibrate stress, you probably are not going to get certain things to pass. You're not going to get the rise times you need. You're not going to get the crosstalk. You also use that same reference receiver to do the calibration of the crosstalk, and I'll show that right now. So the first thing you might run into, by the way, the same drawing was used in the 100G NRZ specs that we're using in 400G as well, so you might be familiar with it. And I know the first time I ran into this drawing, I really struggled with this. I said, what's going on here? The crosstalk's going in the wrong direction. Because you see that crosstalk generator is plugging into the module compliance board, which is plugging into the host compliance board, and then we have termination and calibration right there. And when I actually do the test, because I'm testing a host, I'm going to remove that module compliance board up there. I'm going to actually remove that board, and the crosstalk generator is going to disappear when I do that, right? So why is it there? Well, on the earlier slide when I was talking about compliance test boards, and I said they don't specify the amount of crosstalk coupling that it's actually taken care of in the stress calibration, the only purpose for that crosstalk generator is to determine the amount of coupling in the host compliance board, because that's going to cause eye closure, okay, from the aggressor source, and the aggressor source is actually going to come from the device itself. So you have to have asynchronous data in the counter-opposing direction when you do the stressed eye test, and that output, that transmitter output, because you're testing a receiver input, right? So that output's going to go into that host compliance board, and there's going to be some coupling in that that's going to cause eye closure. So the purpose is of doing this in standard is when you do the calibration, and there's no text that says this, by the way. You'll scratch your head for quite a while wondering why they do this. There's no text in the standard, but this is the reason, is that they're trying to, when they do the actual stress compliance or the stress calibration for the main stress that's going into the input, we want to compensate for the eye closure that's generated by the crosstalk, okay? So the crosstalk is actually generated during the test, and it's inherently asynchronous to the data. And that's specified in all of the standards. All the 400G class standards specify that the crosstalk has to be asynchronous to the data clock. Okay, a BERT can serve as a generator. They've been using the same parts of the same drawing for almost 20 years now, and we didn't even have stressed BERTs when they started doing so. That's why they show they typically show pattern generator with a FM synthesizer off to the side, and you can just think of all of that being replaced by a BERT. So all the modern BERTs from all the vendors have all those stresses built into them, and that's the instrument you use to run the test. So test pattern is PRBS 31Q or scrambled idle. And if you're using a BERT, you really can't do the scrambled idle. You really are stuck with a PRBS 31Q. And then we test for a prefect burr of 1E minus 5. Okay? And this is, since we're testing, this is the module path. Everything is in burr. It's not in SIR. And we'll talk about that when we get to a little bit later in the slide. So this is truly a burr, and the test limit is 1E minus 5. Okay. Questions on that? Yes, Darren.
Steve, I have one question. Go back to this slide here. So I guess two questions on here. One, as far as the crosstalk generator. So we're already adding BUJ, which sort of emulates the crosstalk, and we're adding a crosstalk generator.
Right.
So you're doing both. And my second question, so I guess the question to that is, that's sort of intentional in this calibration. The second question I had was, as far as the BER test, the 10 to the minus 5, is there any sort of plan in the future to use, forward error correction as far as doing the BER measurement is always going to be prefect type BER?
Okay, two questions. So first one had to do with the budge, and that's what I was starting talking about, is why is budge still in the stress recipe? Because the original purpose of budge was to emulate the effect of crosstalk, but just put it directly in the victim lane. And it strictly is, when I ask the question in the standards groups, what I hear is that we don't want to put too much, we need this much eye closure, and we don't want to put too much SJ in there, because SJ will cause the DFEs to fail, right? If it's periodic but not correlated to the clock, that's hard on the DFEs, and so that's the reason that budge is still in the mix. Okay, I don't think that's a good reason, but that's what I hear from the people that write this stuff. So, and the second question had to do with it is prefect. Everything is prefect on this, and quite often in the real test setup, the host chip itself will have a error counter built in. In fact, one of the things I'm finding, and maybe you people could correct me, some of you silicon guys can correct me if I'm wrong, but I'm running more and more of these 400G class SerDes do not even support on the serial side a loop through, okay? And there's a good reason for that, because when we're dealing with PAM4 and the system is running a little bit better than this, in the NRZ days when everything was error-free, we used to think that, well, there's no problem if we keep the channel short feeding the error detector and the BERT, right, then we don't have to worry because there's no loss in that system. But what these guys will tell you, and it's very true, you can play with it in the lab, is that the transmitting process alone in PAM4 has corruptions in it that even with a instrument grade error detector, the error detector is going to get some additional errors just from the process of retransmitting the data. And you do find in cases where some of the first generation, or some of the chips that do have serial loopback, that the air counter in the chip reads a better burr number than the air detector on the BERT does. And again, this is all in a PAM4 environment, and that's what that's attributable to, is that the transmitter has distorting mechanisms in it that are not perfect, right? So the standards are always measuring prefect burr. And when we test modules, we assume that the module is a pass-through device. It has no FEC processing capability. You know, it retimes and resamples the data, but it is strictly pass-through. So it's not correcting any errors and then, you know, sending out corrected serial data. Okay, other questions on the host test? Okay, so the module test is a little bit of the opposite of that. We can go through, but there is an important point with that. So we added a frequency-dependent attenuator that we didn't have. Again, this is the same thing you see in 100G. There's nothing really new here in PAM4. Kind of the same stuff that we were doing with the 100G Ethernet standards as well. So that's basically an ISI channel that the parameters are specified in the standard. Same stress recipe, or similar values. The 5-table frequencies are the same, and the jitter, the SJ amplitudes are the same. You know, starting at 5 UI, working all the way down to 50 milli UI. That's still the same. So, again, we use the crosstalk generator for calibration purposes, again, because we want to take into account the amount of eye closure that we get from the coupling in the compliance test board. So, now one might add, the standard is really interesting because they do say that crosstalk generator has to be the fastest rise time for a legal transmitter, which makes sense if you're really trying to use it, and it would be purpose, you know, in the signal path during the stressed eye calibration. You could make the case that for calibration purposes, I should measure the rise time of my DUT, since my DUT is going to be providing the crosstalk signal, and set that to, you know, if I'm really trying to make the most accurate eye, find out how much coupling I have. And, you know, that's probably valid, but the standard tells you to still go with the worst case. Make it the fastest that it can be. So, and again, you won't measure that crosstalk. You won't be able to measure that without that CTLE and your reference receiver. I was working with one of our engineers. You know, we're working on compliance test software for this right now. And I was just on the phone with them a couple weeks ago and discussing that. And they said, there's no way I can get the crosstalk signal fast enough at the required point. What are we going to do? And that's when I grilled them and found out they weren't using the reference receiver properly. So once we got that, we were able to make the standard. So, okay, so we take all that out for calibration. Now, here's the thing with modules. And again, this is one of these things that this isn't new for 400G. It was required in 100G, but when I go out and I ask people, I find out not very many of them do this. And you really need to do it with PAM4. If your implementation is a PAM4 implementation, because crosstalk is so critical, you really do need, now remember, we're testing electrical inputs here. So we're testing the electrical transmitter input, and we need to have counter-opposing crosstalk. And the way you get that out of a module is you have to drive an optical signal into the module's receive input in order to get that crosstalk signal. Because you're not testing, it's not on the optical side, it's all on the electrical, right? It's after it's detected, and it's just all the routing inside the chipset, inside the module, that the crosstalk could cause a potential problem. And the only way you get that, unless you have some back door that you can feed in an electrical signal otherwise, is to get an optical signal. But you don't have to spend a lot of money on test equipment to do that, because you can just take a second module, and they don't specify this signal at all, the optical characteristics. It just has to be a valid signal, and you drive it with a PRBS 31Q, but you just need a second module. So take a second module, run through, you know, the stuff that Rob showed on the optical compliance test. As long as that output is compliant, then that will serve as a crosstalk generator. Okay. And then you need, and here's another thing that's a change from how you've done this in the past, is in the past, quite often, because your output signal is going to be optical, right? We're testing an electrical input for the transmit input. So my loopback signal, you know, going into the BERT air detector is optical. Now, in the past, what people would do is they would just simply take a second module, and they would detect the signal themselves, right? Or maybe even the same module, and there's your crosstalk source. You just take the signal and wrap it right on through and feed the air detector. Don't do that, because what I was talking about in answering Darren's question, remember with PAM4, the transmitter is part of the corrupting mechanism. So if you try to do that, it's quite likely that you're not going to make a compliance measurement, because we assume an air budget of what the distribution of air is, what percentage comes from, or what contribution of that Burr number comes from the transmitter, the channel, and the receiver. And the transmitter is a healthy part of it, and more than likely, putting it through a second link, you're not going to make the burrs. So what you really need to do is take the optical signal out and go into an instrument quality O to E converter, and then take that signal, electrical signal, out and go in the air detector of the BERT. Okay. Okay, and then the test limit, once again, is 1E minus 5. Simple Burr measurement, nothing complicated with SIR and NAT. So, okay, questions on the module test? Electrical test? So, okay, so we've been talking about the crosstalk generators for a while, and just cover this. I've covered this in past, and I apologize if you've sat through one of my lectures before and heard this, but the standards basically they say that the amplitude has to be the maximum. They're trying to emulate the best transmitter, right? So it has to be the maximum amplitude that a transmitter is allowed to have, and it has to be at the fastest rise time that a transmitter is allowed to have. And again, you need to measure that with a reference receiver that you would characterize. Those numbers for the transmitter are measured with a reference receiver. And by the way, in the current version of the OIF standards, they don't state that for the aggressor calibration. They only state it for the transmitter. And I have comments in on the drafts that are going to be reviewed next week on that very topic, because people don't catch that. So it needs to be at the same data rate, but it must be asynchronously clocked. And why must it be asynchronously clocked? The reason is that you're trying to you basically need a slip phase. So if you asynchronously clock it, the assumption is the two clock generators are not going to be exactly the same frequency stability, and there's going to be a few parts per million difference in their absolute clock frequencies. And the crosstalk only causes a problem when the coupling edge passes through the slicer time window. So, and I'm going to show this with NRZ because it's the same principle holds with PAM4. It's just a lot easier to see the effect with NRZ. So here I'm sitting at my receiver, and I have an aggressor out there, and at some point in time, that aggressor is going to cause some eye closure, depending on how much coupling I have. I have some. But if everything is static in the system and the delays are all fixed, then this point in time is not going to move. And if it occurs the transitioner here, it's not a problem. It's only a problem if it occurs in the slicer where the receiver is looking at the data, right? So now you might sit there and say, well, now wait a minute. In my real system, my Ethernet switch or whatever, this is synchronously clocked. This isn't fair. Why are you making me do this? Because I do have synchronous clocking. Well, yes, you have synchronous clocking, but the delays in your end device are probably different than the delays in your test setup when you're measuring this in the lab, right? And so in the lab, this might always stay here, but maybe in your device, it's the perfect storm and the delays are such that the crosstalk occurs at the worst possible time. So how do we test that? Well, what we do is we put this phase slip in there. So here again, we get eye closure at one point that doesn't cause a problem, but now we're going to slip this phase over time, and each succeeding test, we're going to test at a different place. And there you see, if there is too much coupling that causes enough eye closure to get you into problems and start seeing bit errors, you will eventually cross through that point. So that's the reason the standard calls that out. And it's a big deal because this isn't easy to get. This says you have to have an extra clock in the system. If you have a BERT that has an auxiliary clock out, that typically won't do it. But there is an exception. There is a way to do that. You might be able to do with a BERT, depending on how it's configured. If it's a multi-channel BERT that has multi-channel stress, which a few do, not many, and you can take that second channel and just put in some very low frequency SJ that is more than half a milli-UI, or more than half of a UI rather, of jitter, that makes sure that you cross all the way across the eye, then that'll do the job as well. And then some other instruments that have been out there specifically for this purpose, for the purposes of aggressor generators. It is a synchronous clock, but they put an IQ modulator in one of the paths, and they allow it, they can program it to constantly slip in phase, so it's constantly rotating in phase, and that does the same job. So you can kind of get around that requirement if you have a way to, basically all you want to do is you want to make sure that you're dithering in that coupling edge, so where it occurs, it covers at least one unit interval. And if you do that with SJ, by the way, you should use a very low frequency, as low a frequency as you can, because some situations, when you really get in the perfect storm, it's not just where this occurs, but there's also pattern sensitivity in it too. So you're going to have coupling that only causes an eye failure at one particular point in the test pattern at one particular delay point. And by using a relatively slow dithering of that, you're going to assure enough dwell time so when you're in this nasty spot here that you're in trouble, that if there is a pattern susceptibility, you're going to pass all the way through the test pattern and catch it. And if you have a very, very high sweep frequency, then it might take a long time, statistically, for you to get to that point where the pattern and the delay just line up. So, okay. Oh, and final point. Now that we're working with PAM4, people talk about, well, can I use NRZ as a aggressor? Well, you can do NRZ as aggressor, but you really overstress your part. And Mike Lee of Altera Intel gave a really good presentation about almost 2 years ago, a year and a half ago, at one of the OIF meetings where he did a lot of work on this and showed that you're really overstressing your part with, assuming you have a crosstalk to start with, by using an NRZ versus a PAM4. So yeah, it's a lot less expensive to use NRZ, and if you pass it, fine. But if you fail, that doesn't necessarily mean you failed. So then you might want to you're trading off budget versus engineering expense, or budget versus schedule. Sorry. Okay, so questions on the aggressor. I'm going to move into the chip-to-chip now. This is, again, covered in 802.3bs. It's about a 25, approximately, everything specified in dB. There's a 10 dB channel, a 20 dB channel, and it assumes that works out to about roughly 25 centimeters of electrical length. In the case of IEEE, OIF has different numbers for theirs. So we don't have the concept of module compliance boards and host compliance boards because this is a non-standardized connector. So now it's interesting that when you get to the drawing from it, they show a connector, which is kind of confusing. But the assumption is if that connector is even there, that would be like a daughter card or maybe a NIC card connector on a switch card. But the assumption is that connector is proprietary, so you can't use it as a compliance test point. So compliance points are called out in the drawing. Now, once we go to chip and the longer reaches in OIF as well, we break this, IEEE really started this, we break this into two stress tests. We have a jitter tracking test, or what they call the jitter interference test, which is just pure SJ, and then there's an interference test, which is just injecting high frequency noise that is power spectrally balanced at the far end of the channel, far end of the ISI channel. So that's the input interference test, and then a traditional jitter test, and you'll see the jitter test only uses low frequency SJ. It didn't start out that way. This first came about in the 100GKR4 standard, which is a backplane for 100G. And when IEEE first did this, they had a traditional stress mix, and it was kind of embarrassing. This was actually caught in letter ballot stage, and you'll see why in a couple slides as to why that just flat out won't work. And even this test is kind of marginal with the way it is done. So prior to testing, you need to do the auto equalization in this, and the standard even stipulates that all of the receiver, if the receiver has an auto optimizer for doing its CTLE and DFE, then that has to run before doing the testing. Yes. Question is the jitter tolerance test done at the far end of the ISI channel? Yes. The ISI channel is present for the jitter test as well, but you turn the noise source off, so you're only doing one. You'll see the test set up on the next couple of drawings. So, okay, so interference test methodology. It's typical IEEE where it's cross-referenced back. So 100, the Annex 83 is the 100G KR4. That's the backplane 100G test. And there's a whole list of changes. So they say, follow this test methodology, but make all these substitutions in it. And we run two different tests. In this case, two static tests. We're not sweeping the length of the channel. That's not practical. We do one with a short channel and one with a long channel. And then the first step you do is you have to determine a comm measurement is involved with this, but we also have to determine basically the frequency-weighted native noise in the test system, because that's already present, and we're going to add to that when we add to random interference, and we don't want to stress the parts, so we first make a measurement of native noise in the system. So, and then the equations are all given in the old 100G annex, but they're modified, and the RI amplitude is a flat power spectrum. Now, it's real interesting if you've been following. The very first one of these was done in the 10G-KR standard. I think that's clause 65. And they started out with 1 gigahertz to Nyquist. Then when we went through the whole family of 100Gs, they changed that to saying we're not so worried about the low frequency, and it's always going to be 20% of data rate to 50% of data rate. And now for 400G, it's gone back to the 1 gigahertz. So it's a flat noise spectrum from 1 gigahertz to Nyquist. And in the case of 400G Ethernet, Nyquist is 13.28 gigahertz. Okay. Here's the thing. I touched on this before. Two test patterns are called out in this. The scrambled idle. No, for interference, there's only one test pattern. Scrambled idle, and scrambled idle is scrambled idle, which uses a PRBS 58 as a seed. You probably know that is the seed for that. And then it's two layers of transcoding. We do 466B, and then we do the higher bit transcoding on that. We have to inject the lane markers in it, lane alignment markers, and the last thing we do is take Reed-Solomon 544, 514 encoding. All of that has to be done on the test signal, okay? And a reason which is impossible for BERT to do. No BERT can do that, okay? So how do you do it? You use a golden dot. So you take a second device, you take the transmitter out of it, and just as you did with the optical stressor, you first validate, you do a compliance test on its output. If you prove that its output is compliant, then you use it as the generator. Now, it's okay to do that because all the stresses come in externally in the case of interference. There is no jitter used in the interference test. So pass criteria is a prefix SIR, and has a symbol error rate of 10 to the minus 4. And notice the term SIR. Do not confuse SIR here, and they don't tell you this in the standard. Don't confuse that with SIR thinking of PAM4 SIR, okay, which is symbol errors. No, this is FEC SIR. So the assumption is that, actually where this is measured, it's measured inside the chip, and it's done, with the internal air counters. And it's done already after the D-gray coding, so we're no longer in a PAM4 environment. This is an NRZ bit stream, and the frame size, or the symbol frame size at this point is 10 bits, because that's the standard calls out in the 544, 514 /10, 7, and the 10 is the frame size for the Reed-Solomon frame. So that's what you're measuring, and so that's why the criteria jumps down. You saw it before, it was 10 to the minus 5th, and now it's 10 to the minus 4th, and that's just a nice factor of 10 difference. So,
Question.
Yes. Well, how do you correlate this to the BERT? Well, first of all, the BERT is, the assumption is that BERT's not being used in this test whatsoever. For the error detection, the standard requires that you have air counter in the SerDes that only has to work with that pattern as a minimum. Okay, that's a requirement. So you're never using the BERT as a measurement instrument. So then it gets into the generation. The generation problem, we can't do this in the BERT because this is just way, we would have to do this in hardware in the BERT. Well, that's correct. You have multiple lanes. You have 8 lanes, okay, and you have to because it is striped, okay? So you would have essentially 8 separate test patterns, right? One for each lane. And, but yeah, the BERT can't do it because it requires too much hardware in the BERT to generate that So how do you do it? Why did they pick this crazy test pattern? Because you already have this built into the SerDes. This is the normal data path, right? All you have to start with is, actually you don't even start with a pattern because it's scrambled idle. So all you do is you just nail the data input to either, one of the 4 logic states, right? And then the scrambler is going to work. And the scrambler creates the test pattern, and then this whole string, scrambling, 2 layers of transcoding, lane alignment marker injection, and FEC encoding, that's the normal signal path within the SerDes.
But that's within the SerDes.
That's all within the SerDes, right.
So if you're doing this using a test equipment...
But you don't need test equipment with this, right? Here's the test setup, and the assumption is that it's all measured in the DUT, and because there's no jitter in this, we start with a clean clock. So you clock your pattern generator is the DUT itself, a second DUT, okay? And then we have our channel, and then we have our random interference injection, and then the error counting is all done in the DUT that's under test, the real DUT. Okay, so we don't need any test equipment for this. And this technique works. Now you're going to see, you're almost kind of baiting me here because when we get to you're going to see what the big problem is with the jitter, okay? Jitter test. This is the interference test. So these are all differential signals. I draw them as single-ended for simplicity, but they are all differential. And what does that mean? That means for the RI source that you need a balanced 180-degree phase split, and you have to inject it in both sides. It's not just single-ended, right? Because that would be common mode. You want a true differential mode. So how do you do that? You need a wide bandwidth balun. There's actually a company that they didn't used to have those. I remember baluns only covered octave, and now there are a couple of vendors out there. And if you see me afterwards, I'll give you the name of. I cross-reference them quite a bit, but there is a really good balance source. Or you can use an arbitrary waveform generator. We have our arbitrary waveform generator does this now. You'll say, wait a minute, that's not random enough. Well, the length of our pattern versus the test time in this, the test will be complete before we make one pass through our pattern. So it's random enough to do that. And there is a crest factor specification, and we're well within, we've got orders of magnitude to spare on the crest factor. So you can do this with an ARB. And what's nice about the ARB is you can do the frequency banding. You can contour that without having to deal with any filters, and you get the differential output. That comes for free. So, questions? More? Okay, so how do we do the stress calibration for that? Okay, it's a 4-step process. So the first thing we do is we measure with a spectrum analyzer. We measure the noise output because this is very frequency dependent on this. So we want to know what the spectral noise power of the native noise coming out of the signal generator is. So we make that measurement with a spectrum analyzer unconnected to the test setup. Then we measure the insertion loss all the way through the test channel, all the way from the ball of the chip to the input of the ISI channel. Then we measure the insertion loss of the RI channel from the output of the RI source to the test point. You plug all those numbers into a modified COM calculation that is provided or is referenced in the standard, and that tells you how much power you need in the, actually they specified millivolts. The number comes out in millivolts peak to peak from the IR source, and I'll give you a clue right now. You really can't measure that effectively, even with a sampling scope. Or the best way to measure that noise power is with a RF power meter and just do the milliwatts to millivolts conversion. So, okay.
Again, that RI source had to go all the way up to the baud rate?
Has to go up to Nyquist. Yep, has to go up to Nyquist. There's a few companies that make those. So, and I'm working with one of them to have some, they do them all custom, and there's only three bandwidths involved for covering the 10G, all the 100Gs, and the 400Gs. and I'm working with an applications engineer to have some part numbers assigned so you can just go order them right off because right now you have to call them up and they'll make one for you, but I'm trying to get that standardized. So, why didn't they use another transmitter as the noise source? Well, that number works out. I don't think you can get enough noise out of it. That's the problem. What you want to do, they're putting it at the far end of the channel, and they're using the channel operating margin calculation to set that noise source to the worst. Okay, this might be spec'd at 3 or 3.2 dB is what the COM number is. So with all the channel in there and everything, they want to put the noise in to replicate the worst case transmitter plus the worst case channel. And I don't think you're going to get enough noise out of a transmitter, necessarily out of a transmitter to do that. So it would take several transmitters. And then, who knows what the spectral content of that is, right? So this is a more standardized, repeatable test. You look like I didn't answer your question. They actually use, you can use, if you have enough signal amplitude, you can use power dividers, but usually people use directional couplers because they don't have enough amplitude. But this number works out to be very, very small without factoring in the, if you just looked at it, backing out all the loss through the coupler and the balun, it's only on the order of 12 or 16 millivolts, so RMS. So it's not a very high level of noise that we need. And then, of course, you're going to lose all that. You're going to lose the balun, you're going to lose going through the balun, you're going to lose some going through the directional couplers. Well, again, the purpose of this is I think if your transmitter is compliant, by definition, your transmitter could be worst case noise, but more than likely is going to have some margin and be less than worst case noise, right? So, and then I don't know how it factors putting it at the far end of the channel versus the near end. You'd have to think about that. But I doubt that you're going to get the spectral content. So the idea is there's this COM number in the standard, and the receiver should work with the worst case transmitter and the worst case channel based on what the COM number says. And so now what we're trying to emulate that with the test setup. We're emulating the worst case transmitter and the worst case worst case channel. And so that's what we're doing with the RI in it.
So, do we need a RI source even after the pattern generator?
Yes.
The question is, do we need an RI source after the pattern generator? Yes, it has to be at the far end of the channel. And yes, we do need a random interference source to do this interference test.
So, what is the purpose of the step 1? What are we trying to step 1? So, using spectrum.
Oh, this is how we do the calibration. So, step 1, I want to measure. I have some noise contributed by the test system itself, okay? So that's what step 1 is doing. Step 1 is saying, what is that noise spectrally weighted, okay? Step 2 is, what is the frequency dependent loss through the test setup, because that's going to weight that noise, and all that has to get plugged into the COM model, because at the end, I'm going to have to inject noise that, and I have to factor in all the spectrally weighting, this frequency-dependent effects of weighting on that. So this test really isn't, and this test isn't new for 400G. I mean, this dates back all the way to 10GKR, and it was used quite extensively. Most of the IEEE electrical reaches that are anything but chip to module, anything but the very short reach, has used this technique before. So this is basically how it's done. Okay, so now let's move over to the jitter test. So I said this chip-to-chip has both an interference test and a jitter test, and this is where we run into the issue, because now what we do is remember I said that it only has a low frequency SJ in it. So now what we do is we use an RF synthesizer in front of that compliant compliant DUT to do a pattern generator and feed the same thing. So the question was, do we keep the ISI channel in? Yes, we do. It explicitly says in the standard that it's the same test setup, but I remove the noise sources, the RI sources. And in the ease of calibration doing your test, you might even leave them in there and just turn it off, because That way you don't have to account for the change in channel loss that you're going to get when you pull that directional coupler out. So once again, 5 discrete tests with pairs of SJ frequencies and amplitudes associated with. We do this only with a 20 dB channel, so it's only the worst case channel, and you'll see that's where the calibration is for the 20 dB. COM is measured to set the amplitude for the worst case in this. Okay, so that's how we set the eye closure up on this. And until very recently, the standard said that it was the very same test pattern. Use the same test pattern as the interference test uses, which is that scrambled IDO with the lane alignment markers and the double transcoding and effect encapsulation that no BERT can do, okay? And I pushed really hard on the committee, working group, and forced them to make a change. And if you see the version 3.1 draft, it's only been out for a few weeks, it allows you to use a PRBS 31Q. And the reason for that is that allows you to use a BERT as a pattern generator. Now, you're still using the air detector in the chip, and this requires that the chip now has 2 different air counters, one looking for that scrambled idle pattern, the other looking for a native PRBS 31Q with no FEC on top of it. And the reason you'll see that is you have this problem with the SJ passing through the compliant DUT. You're going to get some jitter tracking by the POL in the reclocker. So very careful calibration is required. That's kind of a big pain. And then this is the problem with this, and I have to raise my hand. I'm the one that introduced this. So now we have 2 test methodologies for this, and they give 2 different test results, which is unfortunate because we have the prefix SIR. Again, this is SIR related to effect frame of 10 bits, or we have 10 minus 4, or 10 minus 5 if you're measuring BER, just pure bit error rate, okay? So why did we introduce this in the standard? I'm not happy about it. Well, here's the problem right here, okay? So this is the prescribed test method. And again, this came out, the first time this came out was in 100 GKR. And originally they were going to pass all the stress through it. And it all gets into this problem here, this reclocker, right? Because you can't pass any high frequency stress through that reclocker. It's all going to be gone. And not only can you not pass high frequency stress through that, it has problems with the low frequency as well. There is going to be some point where the POL tracks, right? And it really is impossible for a chip guy, because you don't want to just measure compliance pass fail. You want to know how much margin you have. So you want to you want to do a jitter tolerance test and run this jitter all the way up until the part fails, right? So you can't do that with this technique. But not only that, if you look at that table, depending on where your loop bandwidths are in that reclocker, you might not be able to drive enough stress through to even do the compliance test. And today I've worked with many users doing 100 GKR that have this very problem. And what do? They get a lot of chips back of 100 or 200 chips, and the first thing they do is they go and they measure the POL bandwidth of the reclockers, and they cherry pick the one that has the very lowest tracking frequency, and that's the one they use for their compliant DUT, because that's the only way they're going to get enough stress through to even do a compliance test, let alone a margin test. So this is a really bad problem with this test methodology, and that's why I really pushed hard on the standards group to allow us to use a test pattern. Now, people say, well, you're with an instrument company that sells a very expensive BERT. Yes, that's true. That wasn't my reason for doing it. My reason is, what do I do when I got a customer on the phone or a user on the phone, and they say, how do I do this compliance test? I don't have a chip in my lab that I can drive enough jitter through to do the stress calibration of the required stresses. So this is a technique that allows you to replace the compliant transmitter with a real BERT, and does that. So that's what the alternate pattern does. But unfortunately, it's a bit more stressful than using the SIR measurement. The numbers are not going to correlate. You factor it by a factor of 10, but it's not going to perfectly correlate, because when you go through all that decoding stuff, you get some gain of air performance when you're using the scrambled pattern versus using just the raw QRBS 31Q. So in my opinion, this is still a problem with the standard. It needs to be worked out, but we're still struggling with it. So, because I don't like two test methodologies that give different results. Yes, Lewis?
Can SSPRQ be used to reduce test time and pattern length instead of 31Q?
Question is, can SSPRQ be used? No, SSPRQ is only used today. It started out being used in some of the optical stresses for the stress receiver, and it is no longer used. It is only used for TX measurements, for output measurements. So it's not called out. So this pattern you can generate with a BERT. This isn't a problem because this can be hardware generated. So it gets by the problem with all the scrambling and encoding. But it does give a different test result because of the fact that we're not measuring it with all the transcoding stuff. So yeah, it does not scale precisely. So it gives you a slightly more stringent. And it even states that in the standard. The wording in the standard says that this result will give you a slightly more stringent test. Yes?
Is that, in the previous slide, you said the pass criteria for SCR is
1e minus 4 or Burr of 1e minus 5.
Is that Burr of 1e minus 5 in the standard?
Yes, it is. This is the actual wording in the standard is that it's 1e minus 4 and 1e minus, SIR of 1e minus 4 and a Burr of 1e minus 5. And they do state in the standard, Mike Dudek's words, that this is a slightly more stringent test. So they warn you that you're not going to be apples and apples. So, okay, so let's move on to CD. It's funny, when I put in for we were planning a seminar months ago, and I did a similar talk on this at DesignCon, and we have to squeeze it in 40 minutes. And said I don't even have time to do backplanes, so I pull that out, and I just skimmed over everything so fast that people couldn't really comprehend it. So now I've got the time to do it right. And I wanted to put this in, and then I was just digging into this a few weeks ago when I was finishing slides, and I found out it isn't done yet. So there isn't even a test methodology called out. But I think you know what the test methodology is going to be. So, and the reason is because there's enough things in there that are referenced. So you know, the channel requirements are all the same. So all the requirements are based on what I just showed you. 120D is the chip-to-chip standard in the 802.3bs, and it's probably going to apply to backplanes because that cross-references a 100G backplane. So they're starting with a backplane, they're going to a medium reach channel, and now we're wrapping around to a faster backplane spec. So list of changes. Designated compliance test boards are required again with the S parameters specified. And then Rob had a similar picture in his slides. So they conveniently allow you to de-embed. So you're building this test fixture in there that brings out from your package balls to a test point, and all those S parameters are specified in the standard. So that's already locked down. That part's already done in there. So test methodology isn't done yet, but I'm going to assume if they're already calling out, they already have the Burr requirements, and they already have all the cross-references for what the channels have to do. So it's probably safe to assume the test methodology is going to be based on what we're doing and what I just showed you in 120D. Okay, so yeah, and you have to be careful where you're cross-referencing here because things are changing. So. Okay, link training is required, just as we had to do with 100G. You have to do link training before you begin doing this test. The backplanes have a more complicated link training. It's a lot more complicated than the auto negotiation done in a receiver by itself. For those that don't work in backplanes, the assumption in the chip-to-chip specifications are the design engineer knows where chip A and chip B are located on the circuit board. The designer knows what the trace length is or the loss between chip A and B, and things like the de-emphasis presets are, put in the software on the power-up, and they're not interactively tuned. The receiver does some auto optimization with its DFE and possibly CTLE gain as well, but typically the transmitter in a true chip-to-chip application does not vary. That's all hardwired because they know what the channel losses are within the range that they can tune the receiver, and that's just programmed in power-up. But when we deal with backplanes, that's a different situation because the user could be plugging the daughter card or the second card in slot 1 or slot 13, and obviously, every slot along the way is going to change the channel quite a bit. So in all the KR standards, there is this complicated process where we communicate through the back channel, and the receiver tells the transmitter what the de-emphasis settings or pre-emphasis settings have to be to get to the optimum eye opening. And actually, it's not eye opening; it's actually making a burr measurement during the test, and that all has to be done. When we did 10 GKR, we didn't require you to do that because we knew what the test channel was, and we knew roughly what the de-emphasis had to be set for. So the test procedure just said hardwire the de-emphasis to these settings and use a BERT. Okay. Now we have to do link training, and once again, the standard is assuming that you're using a compliant DUT in place of a BERT for this. But it's kind of tough with a BERT because the same problem with a reclocker, you're not going to, or without a BERT, you're going to have this same problem. And we are stepping up and addressing this. We already have support for 10 GKR, 25 GKR, and 100 GKR4 are going to be out in August, and we'll follow as soon as the standard is done. We'll have the 400G out as well. So, BERT does support the link training. That makes it really convenient because now you can test with a BERT. You can do everything with a BERT in the system, and it makes stress calibration a lot easier than having to deal with using a compliant DUT. Okay. So basically what the test methodology is going to be. Okay, questions on that? Again, we don't have a published spec yet, so I don't know for sure that's how it's going to work. But given the fact that everything else is based on Clause 120D, which is the 400G chip-to-chip, I assume that's going to be the case for the backplane as well. Okay, so that's everything that OIF and CI says. CI is very similar to what Ethernet is doing, and that's what is required. But what about some other characterization testing that you might want to do? These are not required in the standards today, and the reason is because the standards typically, they start with the last generation and they just move on and they only put in what they need to. And generating the stress for some of these can be difficult to do, and I think that's the reason the standards went away from it. But there are, if you're a SerDes guy or a chip guy, you might want to do these to really validate that you're truly interoperable, because they are required. These impairment mechanisms are specified in the transmit measurements, so there's an assumption that the receiver can tolerate them up to the limits of what they allow a transmitter to have. So thorough characterization will include these tests, and the two ones specifically are linearity tests. Now, IEEE doesn't do linearity, but OIF does do linearity tests, okay? And linearity, as Rob said, that's the size of the relative eyes in there. So you can have three different states. You can have it just where the center one grows, or you can have it where they're stacked, where the lower one or the upper one is the smallest, and they all go through. And then the other cases with eye skew, okay? And eye skew comes out. You saw, actually, I didn't know if did you catch that? Was that in your presentation, Rob, where you actually showed an optical eye? Yeah, did you see the eye? I could see the skew in that, just sitting where you're sitting, yeah. The skew's in there. So the skew comes about because VCSELs, the higher the voltage you drive into a VCSEL, the faster the laser turns on, okay? For those that don't work on optical modules, that work on primarily chips might not realize that. So the upper eye is going to arrive in time before the lower eye does. And you really need to deskew that. It's typically done, an attempt to do that is done in the drive of the optics, but there is a skew, or an eye skew spec, but it's kind of hidden in there. It's done in, remember when Rob was showing, he talked about all those measurements are all relative to the center eye, and that kind of implies, when you do your eye opening, your eye height, and your eye width, you're really encompassing a skew spec in that, because even if the individual eyes themselves have nice opening in them, but there's significant skew, when you're only referencing it to the center of the center eye, then you can only tolerate so much skew before you start seeing eye closure caused by the skew and not because of the individual eye itself. So these are things that you really should look at in a receiver if you really want to shake it out. And again, for OIF, you're going to have to do the linearity tests. And we have BERTs that can do the linearity really well, and AWGs can do the skew. And I'm sure that Steve is going to show you the linearity. I hope you can show linearity really quick on that. So that's kind of... Okay, so any questions on electrical before I move into optical? Okay, so let's talk about the optical test, so generalities of it. Test methodology with the electrical, in every case, the error counting is done in the chip, okay? But with optical, it's not done in the chip because we assume, the assumptions being made by the standards organizations that we don't have error counting capability in the chips, in the modules. I understand that some of them have some limited capability today, and probably the next generation will have a lot more, but today they wanted to make the assumption that everything's passed through. The other thing is they don't deal with FEC, because again, optical modules do not process FEC, they simply pass it straight through. So they do retime, they do clean up the signal with sampling and rebuild it, but they don't decode FEC and correct the errors before the signal is retransmitted, okay? So that's all a pass-through. So because of that, it makes life really nice, because with that being the case, they just took FEC out of all the testing whatsoever. So test pattern exclusively is answering Lewis's question. Right now we've gone to PRBS 31Q everywhere. So that is the test pattern used for stress in all of the opticals so far. Fiber channel hasn't gotten far enough to do that yet, but so far all the work that's being done in optical, that's what we assume. So scrambled idle, I put in scrambled idle in there. There's a few legacies that still say that, but they're all moving to PRBS 31Q. So, okay, crosstalk aggressors are mandatory. And again, this is something people haven't been doing, and it's not only on the receive side, it's on the transmit side as well. So Rob was talking about when you do on the electrical, but as well as in the optical side, you have to have a aggressor. And that gets kind of complicated when you're even doing the TX measurements, with a DCA on the optical side, because now you have to put a demultiplexer in there, because you only want to look at the eye that you're specifically of the lane that you're testing. But you do have to have all the other lanes in there, and so all of those optical signals are going to be superimposed on top of each other. So asynchronous test data and transmits must, so you got to go in both directions. So the alternate lanes as well as all the transmit paths have to be driven. Now that can be a lot of generators. I'm going to show you how to simplify that here in a bit. So here's a basic test setup, and there's two of them because one of them is dealing, remember the FR4, FR8, LR8, LR4 are WDM. So these are one fiber with multiple wavelengths, multiple lasers, right? And so here's the test setup on this. It's a redo that we've been doing for years and years. And I never liked it with a 10G and 100G, and particularly with a 100G, because there's a lot of stress things that the IEEE, in my opinion, was pretty bad, because they put parts in the stress, actually in the block diagram, and they did not define the values. They did not define the low-pass filter, and they actually had a limiting amp in there that was trying to do data-dependent pulse width shrinkage, which you no longer have in modules. Once you put reclockers in the modules, you don't have that phenomena as a real stress phenomena in the final link, so you didn't need to put it in there. But IEEE still put that in. They carried it over because, again, they step and repeat from the 10G days. And they didn't call out those parameters. It didn't tell you what that filter value had to be, and they didn't tell you any of the information on the limiting amp. And I always thought that was kind of bad, because those directly impact the level of stress that you're testing the part to. So they require the user to kind of understand the application space and make some assumptions on what those values have to be. And when this time around, Jonathan King from Finisar did some really good work with the standard, and went in there and just really, he did two things. First of all, he got rid of the limiting amp, which we don't need anymore. We didn't need it in 100G either, but it was still there. And And then he specified both the low-pass filter and the sinusoidal interference frequencies, which were not specified before. So now I think the test is going to be a lot more repeatable because there's no interpretation for the user. So this is the test setup, and it's kind of messy still in some ways, and then we do need the aggressors. Remember, we have to do all the alternate lanes, which is what we're doing up here. So this is all, if we're doing the 200G where we got 4 lanes or four wavelengths, we have to put 3 in as aggressor. If we're doing the 400G case where we have 8 lanes, we have to put 7 aggressors in there. And then we have to drive all the transmitters, okay? So pretty ugly test setup. But crosstalk, again, is necessary because it's not an optical phenomenon, it's an electrical phenomenon after it's detected. And you have the ability to really simplify that quite a bit. But it does require that you have the ability to turn off the transmit laser on the lane that's under test. And here I will show the looping back. So now what we did is we just replaced all of that stuff with putting a coupler in instead and using the DUT itself as the alternate lane. So if you could turn off the laser, if your device allows you to individually turn off the transmitter lasers, so all you have to do is turn off that laser and you just drive that into an optical combiner, and now you eliminated the 3 or 7 additional tunable lasers and the multiplexer. Okay, and then we can go one step further, and instead of having separate aggressor generators for each of the 8 paths going through, we just go down to 1 aggressor generator, okay, and we simply loop it through. So we just take the receive output and feed it into the transmit input on the next lane. So great simplification for doing all this. So basically you get down to the device itself. If you have this capability to turn the laser off on the lane under test on the drive side, then you greatly reduce the test setup as far as the crosstalk goes. Okay. And we do have to switch the lane of the device under test. Okay, so each wavelength is tested independently. We only do one at a time with all the aggressors in place. And a BERT is used to measure it because, again, we're assuming there's no error counters in there, but we can do a PRBS 31Q without any problem. So don't forget to change, when you move lanes, don't forget to change which lane you're feeding the error detector, because otherwise you'll be measuring the burr of the aggressor signal. And don't think that hasn't happened before. Okay. Pass criteria. Now this is kind of funny. Pass criteria is a burr number that we measure with a BERT, and it's 2.4 e to the minus 4, but it assumes a more or less random distribution of errors. So if there's something going on that clusters all the errors together in one frame that would cause the Reed-Solomon to fail, then the standard requires you to do a frame loss measurement computation, and that's quite a bit more complicated.
Could you put one more sentence around that? The frame loss ratio measurement?
It requires you to do frame loss. It's an Ethernet frame loss ratio measurement. Okay, and this is a complicated thing that BERTs today aren't doing but can do, and which means that people are looking at how to do it. And basically, you need to cascade 3 counters in the error detector. So what you do, you basically say in a Reed-Solomon frame, I have a threshold of how many errors I can correct in that frame. So the first thing you have to do is synchronize with a pattern and find out where you are in a pattern alignment, okay? Then I start a counter that counts the number of bits in that frame. And then I have another counter that's counting burr, okay? And if burr exceeded the predetermined threshold, depending on what my Reed-Solomon algorithm is, then that's a frame loss. So I lost because if I exceed that number of bits within that Reed-Solomon frame, the entire frame is non-recoverable. Okay, but that's a third counter that just gets an increment. And you just run in that mechanism for the entire test, and then you count at the end, you count how many bits went in and how many, from that you can mathematically determine how many frames went in, and you determine how many of them would not be correctable by read-cell. And all of this, by the way, all of this is done pre-FEC. Okay, so we're not looking at post-FEC, but this is predicting what would come out of the a post-FEC air count. So, okay. And air location analysis using a histogram will give you a likelihood of this, but not an absolute guarantee because it is a histogram, right? And the only time you get a frame loss is when those, and it's not necessarily a burst of adjacent airs, it's just within that frame, okay? And if you use air location histogramming, pattern position histogramming, I'll try to avoid using the trade name, then you could have one pass to the pattern, we get one error, and then 1,000 passes the pattern error free, and then another pass to the pattern and I get an error right next to it, okay? Now I start seeing that histogram go up with a whole cluster of errors in the same place, but those are not necessarily in the frame, so those might, it indicates a likelihood, but not necessarily a guarantee that that was a real frame loss. So, okay, the module people here probably know how we're doing this today. It's very painful, right? We're measuring in a real-time scope, we're digitizing in a real-time scope, and we're building the air detector in MATLAB and doing all the math. So, okay, so I'm almost finished here. One more wrap up on, now I'm going to move to the DR4. So DR4 doesn't have the WDM. This is the lower cost, lower reach, 4 lanes or, always 4 lanes of fiber optic running in either 26 gigabaud or 56 gigabaud. And so this is the optical stressed eye setup for a very, very similar thing. Again, Jonathan did work on this part as well, got rid of the limiting amp, specified the SI and the LPF, which are necessary. Now, there is a difference between 200 and 400 because the optical, there's always 4 lanes on the optical side. It's always DR4, even in 200G. But as I said, it's optically 56 gigabaud. In the 400G case, it's 26.56 in the 200 case. So this is showing the 200 case, and when we do the 400G, electrically we don't jump up to 40 to 56 gigabaud. So we're still using that same AUI, that chip to module AUI test that I started the very beginning of this with. That's the same test, but now we have 2 lanes. We have one optical, 56 gigabaud pattern going in, and we're looking at the data interleaved on 2 electrical lanes coming out. Okay. Okay, and you can do the same stunt with the aggressors. Okay, so in fact, you want to do that obviously in this, and it's so natural in this. We just feed we take the receive outs of the, feed that in the transmitter, take the transmitter outs and feed it into the receives to do the alternate lanes as well as the back channel, and that gets us all of the aggressor signals with one generator. Okay, and again, it's pretty much the same thing that we had with the LR and FR. Each lane is tested independently. BERT measures the output from the device in our test. It's an electrical signal. But remember, with the 400G, you've got 2 lanes to deal with, so you have to take the pattern and cut it apart to do that. And same pass criteria, very same pass criteria. 2.4 E minus 4 is the with the assumption that the errors are randomly distributed, and if they're not randomly distributed, then it's a 1.7 e to the minus 12 frame loss ratio requirement. No difference between the FR and the DR with that. Okay. Okay, that's finishing all the compliance tests in way too little time, but just kind of give you an overview of the basics of the test setups and requirements. And obviously, when you get into it, you might have more applications questions, and feel free to work with us, our application support people, if you run into challenges. So any more questions on the input testing before I just do the general summary? So, yeah. change, the fact that we have a full house today is not surprising because moving to PAM4 is very revolutionary. It's a big change for just about everything, not only in the test area but in the chip design area as well. And we're seeing it both electrical, optical testing. Keysight has good solutions for the simulation, as we started to talk with. We talked about output measuring. These are changing constantly, so we're seeing new stress types coming in. We're seeing new optical measurements being, I think Rob talked in there a couple times where the standard has made a very recent change, and it typically takes us about 1 quarter to catch up with that, and then we'll have it implemented in the software. So linearity is something now we need to do with stress input testing on the OIF. It does require it. I didn't really go into that in depth. It's not a swept test, it's just a static test. So it's just when you do in OIF, when you do the stressed eye test, you simply change the amplitude levels of the eyes to start with, and you run the test with a nonlinear eye. So we can put a whole list of every single one of these parts of our solution set. Has a link page in Keysight, but if you don't want to memorize that whole list, because that's on the next couple of slides, if you have any questions on PAM4, just remember there's one website, keysight.com/PAM4, and that will get you to everything we have in there, and then you can search from there for your specific area. So that, open up for questions. And just talk about the solution set. So, we're getting back into the commercial again. ADS and system view, Rob touched on some of the capabilities of that. Again, we're not the experts. The experts are back in the factory on that, but we just wanted to show you the completeness of our solution set. For a TX side, we have real-time and sampling-based solutions covered in here, and talk about the BERT for input testing. And Mike already presented his finds for the PTLS. So, okay, and then we're going to finish with a demo that Steve Reinhold's going to do here with the new BERT product.
It's our newest BERT platform, 64 gigabaud NRZ or PAM4. Consists of, here's the main capabilities. It's really highly integrated. So in the past, people applied NRZ BERTs to create PAM4 signals, and it required a lot of external hardware. It was pretty complicated, a lot of fiddly cabling and tuning of the timing and everything. But now we've integrated, so it's really easy to switch NRZ to PAM4, built-in de-emphasis and things like that. It consists of 2 main parts, the pattern generator, which we call the M8045A. You can get it in a single or dual channel version, again, built-in de-emphasis. We have all of the jitters that you need to do some of the stressed eye testing that Steve talked about. We've incorporated a remote head, because at these speeds you don't want to lose all your signal in the cable, so we get it out close to the device under test with the remote head. And if you see up here, we have little short 1.85 millimeter cables, and we publish all of our specs at the end of those cables. And again, NRZ and PAM4 switchable by software. That's the first thing I'm going to show you when I demo this thing. We have the air detector is a single slot module that's above the pattern generator, which is a 3-slot blade. Again, native PAM4 NRZ air detector, so you don't have to split the signals into multiple NRZ detectors. And we're working on equalization and clock recovery for that. A couple more details about the pattern generator. It's this 3-slot module in the bottom there. We have, it says 3 taps, there's 4-tap de-emphasis built in. We have level nonlinearity. So Steve talked about the need to do level nonlinearity, and I think the actual spec is, the OIF spec is 0.67 is the ratio between the biggest and the smallest eye. And not only do you want to create that 0.67 ratio, but I think the bottom one's the biggest, the middle one's medium size, and the top one's smallest because of the way the electronics and the optics work. So you want to vary those things in a very specific way, and you want to go beyond compliance. So hopefully, if I remember, the second thing I'll show you is how you create linearity testing with our box here. We'll just move on in the interest of time. Quick look at the eye diagram. We'll be looking at that live. That's a 28 gig. That's a 58 gigabit NRZ. 58 gigabaud PAM4. That was the same signal that Rob was using earlier in his transmit demo. Our error detector, we have a single channel error detector per single slot module. So if you wanted to create a 2-channel BERT, you'd buy 2 of those modules. True real-time symbol error rate on PAM4 without any post-processing. So some competing solutions use multiple NRZ detectors and they're pattern length limited. We're not pattern length limited. We can go to PRBS 31Q, or we actually have PRBS 51 built into our BERT. Steve talked about the actual requirement for incorporating on-chip error detectors. And so many of our customers that have bought these, they've bought the pattern generator, but they've used their own on-chip error detector. And we've actually incorporated into the GUI the facility for doing that, so you can do a traditional jitter tolerance test where you're changing the jitter and measuring BER, changing the jitter and measuring BER from within our GUI, but you're actually querying your own on-chip error detector. So that's not only a requirement of some of the devices, but some of our customers have saved some money by just using their own error detector and incorporating it into the GUI driving the BERT. And then lastly, Steve mentioned that we use real-time scopes for error detection in some of these very high BER environments. And we're integrating the control of the real-time scope as the error detector into our BERT GUI software. One of the interesting features of our error detector is we're able to display the symbol level that caused the error. So in the past, optical people in particular were concerned with, were they errored ones or errored zeros? Were we seeing errored ones or errored zeros? Now it's, which of the 4 symbol levels is causing the most errors. And that can help you get to the root cause of the BER challenges you're facing. And so I hope to demo that as well. I took a quick shot of it as I was setting up for the demo. We've got a great GUI. Unfortunately, it's the high-tech things like the audio and the VNC connection between these that stymie me. We're constantly working on super high-speed, high-tech stuff, and then it's the simple stuff that causes problems. So what I'm going to do is I'm just going to alternate between the scope and the BERT GUI. So, but the GUI that we've implemented for the BERT has lots of great features. You're able to show virtually everything that's going on inside the BERT on one screen. You can customize it. You can drive a 4K display if you'd like. Leave various windows open, measurement windows and control windows open, just the stuff that you want to see inside this, again, relatively complex instrument. Steve talked about a couple things. One is that you can use an AWG for generating interference or as a noise source. We have 2 flavors of AWGs that we recommend in this space. One's an M8195, which is 65 gigasample, has 25 gigahertz of bandwidth, and it's got up to 16 gigasamples of memory per module, so it can hold these really long patterns that can create things like good crest factor RJ. The other benefit of AWGs is they can create the skew that we saw in the real transmitter. You saw it was skewed horizontally. The BERT generator, we can kind of skew things vertically with the linearity test, but the horizontal skew requires an oversampled architecture like an AWG. So there is a good reason, actually there are multiple good reasons to do this, which is incorporate an AWG into your BERT setup. One is for generating the random and sinusoidal interference where you're injecting at the end of the channel and using the AWG as the source of that. Second is if you're going to do the horizontally skewed eyes, if you're going to do a skew test on your receiver, you can use the AWG as that source. And you could also use it these channels are cheaper than BERT pattern generator channels, so you could use it as aggressor traffic or crosstalk source. And I think that's it. So that's it for my slides. And now I'm going to see if I can work the video here to show you a demo of this. So now I'm going to look away. Forgive me. I'm going to look at a small screen with my specs, but you're going to see the effect of what I'm doing on the screen up here. So this is our pattern generator signal. It's running at 25.78125 gigabaud PAM4, and I have done a very unsophisticated setup on the scope because basically that's as good of a scope driver as I am, but I'm wanting it to update fairly quickly so you can see the changes I'm making on the GUI. So the first and most fundamental thing and kind of a profound advantage of this BERT architecture is this. NRZ PAM4. So that takes, hours of tweaking and tuning when you're trying to build your PAM4 setup out of NRZ BERTs, and we just do it native. We talked about linearity tests, so here's how we can create linearity. I can change any of those levels independently. We also talked about de-emphasis, so I'll go down here and I'll add some de-emphasis. And this is what a PAM4 signal looks like with de-emphasis. Sorry, it's kind of dim and blurry, but each of the levels, that was post-cursor tap. Oh, a scope guy can't. He can't stand it. He can't stand it. I'm abusing his product. Anyway, a PAM4 signal with de-emphasis. I just increased the post-cursor tap de-emphasis, and you'll see 4 trajectories per signal. And you saw earlier when Rob drove it at 53 gigabaud. I'm not going to do that now because my error detector presently only goes up to 32 gig. So I'm going to show you some error detector features, but we can drive the pattern generator either in NRZ or PAM4 all the way up to 64 gigabaud or 128 gigabits per second. We have, I'll flip over and show you the GUI. We have patterns, again, up to PRBS 51 or user pattern. So if you're going to put like a custom pattern, your own pattern, or SSPRQ, we have 2 gigabits memory for NRZ or 1 giga symbol of user memory for PAM4. So you can put some fairly long patterns into the pattern memory. And last thing I'll show you before I flip over and show you the error detector and the GUI is let me turn on some PJ. Yeah, there's some jitter. I finally got some jitter on there. So we have all of the standard jitter controls. We have low frequency, high amplitude sinusoidal jitter, high frequency sinusoidal jitter. We call it PJ. Two sources that go up to 500 megahertz. We have random jitter, we have bounded uncorrelated jitter, and we have f/2 jitter. So let me flip over to the GUI, turn the jitters off so I don't confuse myself. All right, so the controls that I was just manipulating were the data output controls. So if I scroll up here, you'll see the things that I was doing. PAM4 NRZ is as simple as that. The linearity controls, we have 0, 33, 66, and 100. I just incremented that to show you the linearity test. So that's any of these controls, like our jitter controls. If we click on them, we get a window that open up over here. If we'd like, we can dock that window. And then, we can have as many of those windows docked on our screen as possible. So if you have a lot of screen real estate, you can turn on a view of every single thing that you'd like to check within the BERT. You can open up multiple system views. So this is a system view of our pattern generator module. This is a system view of our air detector module, which are block diagram kind of views, sort of easy to look at the signal flow. And then we can also open up measurement windows. And what this is here is an error ratio that I just very quickly ran a few minutes ago. And what I did was I let it run error-free for a while on this PAM4 signal. Then I moved one of the thresholds until I started inducing errors, and it turns out that all of those errors ended up on symbol 2. So you can see symbol 0 error ratio, symbol 1 error ratio, symbol 3 error ratio are all 0, and all of that little blurb of errors that I induced showed up on symbol level 2. So that's one of the cool features of doing the native PAM4 detection. You can easily show which level the errors occurred on. Question? Absolutely, yeah. There are multiple ways to control this via automation. One is just the normal Skippy automation. You can control it from the outside world from an outside controller. There's also a Python scripting tool within the bird itself that allows you to run your own custom scripts, and it's in the same vein as, let's see, it's you can also you can execute Skippy commands on the fly. The DUT control interface, that's a little Python scripting window. That's what that's where you would write the commands that query your air detector. So your on-chip air detector. So there's a whole lot of flexibility built into this GUI. Any other questions on the M8040 high performance NRZ PAM4 BERT?